Welcome back, and this lecture is going to be on sequences. Sequences, in short, is just an ordered list of numbers. They could be ordered positive and or negative, but that's just the gist of what a sequence is. There are a number of things that you could do or look for with respect to sequences, and for that you should read through just this first page summary to get an idea of, for example, how you might show whether a sequence is convergent or increasing or decreasing. You could also make use of some theorems, such as whether when the sequence is oscillating between two numbers, or a unique theorem called the squeeze theorem might actually be useful. So I'm going to progress through the examples here so that you could see how some of these things can be applied and get a better sense for what sequences are. In the first problem here, the task is to write out a list of values in the given sequence. So for this first one, the sequence of n from 1 to infinity, this is just going to be, well, when n is 1, n is 1. And when it's 2, it's 2, 3, 4, onwards. And that is what that notation on the left by the A represents. B, here we're looking at the cosine n pi over 6. And when n is 0, that's the cosine is 0, which is 1. When n is 2, we have the cosine of pi over 3, which is root 3 over 2. And when n is, I skipped one. When n was 1, that's going to be cosine pi over 6, which is root 3 over 2. When n is 2, we have pi over 3, so cosine of that is going to be 1/2. And then 0, and then negative 1/2, negative root 3 over 2, negative 1, and by periodicity, it just keeps going back and forth. And that's what that sequence looks like. So that's probably the simplest thing that you could do with sequences, is to just list out the values contained in that sequence. More challenging is going in the opposite direction, like in problem 2, which says find the formula for the general term an of the following sequence. And so over here, we're given a list and we need to figure out, is there a way that we can rewrite these like the terms that we had inside the curly brackets in A and B in problem 1. And so what I tend to do when I'm faced with a challenge like this is I try to view patterns. And so I see that the bottom is always 1 larger than the top. And I recognize that the top is always increasing just by 1. So it's counting numbers. And so I recognize that I can view this as n over n plus 1, where n starts at 1 and goes to infinity. And so what's inside here, this n over n plus 1, that would be my an. So that's an easier example. The part B is a little harder, but you could still look for patterns here. And so one thing that I notice is that the terms are alternating. And so I recognize that I'm probably going to have a negative 1. And for now, I'll just write n, but it might be n minus 1 or n plus 1, something along those lines. But I'm just getting that alternating term in there. And then I see that the top is increasing by 1, starting at 2. And so if n is starting at 1, then I might use n plus 1 on top. The bottom is squares, so we've got 3 to the first power, then 3 to the second, then 3 to the third, 3 to the fourth. And so I see that we've got 3 to the n power. So let's think this through to see if there's anything we need to adjust. I'm starting n at 1, going up to infinity. So when n is 1, negative 1 to the 1 is negative. Then 1 plus 1 on top is 2, and 3 to the 1 is 3. So that works for the first term. When n is 2, negative 1 squared is positive, and we've got 3 over 3 squared, or 3/9. When n is 3, we have negative 1 cubed, which is negative, and then we've got 4 over 3 cubed, which is 27, so 4 over 27, and this setup looks like it is going to work. And again, what's inside these curly brackets, that is our an. This isn't necessarily the only answer. It could change depending on if you're starting at n is 0 or maybe n is 2. And so there are slightly different ways that you may go about getting the answer, but it should have a form very similar to what I've written here. Let's take a look at problem 3. Problem 3 says determine whether the following sequences are convergent or divergent. And so in order to do that, we need to look at the limit of the an term. So the limit as n goes to infinity of n over n plus 1. That's going to be infinity over infinity, which by L'Hopital's is the same as the derivative on top over the derivative of the bottom, which is 1, and that limit is 1. So since we have a finite limit, that means that this series or sequence is convergent. Now let's go through the same idea for the second one here, part B. We want the limit as n goes to infinity of n over the square root of n plus 1, or n plus 1 to the half. And so over here, there's a few tricks that you could use. You could use L'Hopital's again, or I am going to bring the n on top into the square root, and I'm going to write this as the limit as n goes to infinity of the square root n squared over n plus 1. And if I multiply top and bottom, if I multiply the top and bottom by 1 over n squared, so essentially I'm multiplying by 1, that gives us the limit as n goes to infinity of the square root. On top we have 1, on bottom we have 1 over n plus 1 over n squared. And what I recognize is that 1 over n goes to 0. The limit as n gets bigger, that goes to 0. And the 1 over n squared also goes to 0. And so we have 1 over 0, which means that this limit goes to infinity. And so this is divergent. Continuing, we've got part C, and we're looking for the limit as n goes to infinity of the natural log of n divided by n. And so as n goes to infinity, the natural log goes to infinity, and n on the bottom goes to infinity. So by L'Hopital's, this is the same as the limit as n goes to infinity of 1 over n over 1, or just 1 over n, and this is 0, which is a finite value. And so that tells us that this sequence converges. And what about part D? D uses the example from 2 part 2. And so that is 2b that it's referring to. And that's the sequence that we had created here. So let me fix that. This is 2b. So this is looking at the limit of the an term. So as n goes to infinity, of -1 to the nth power times n plus 1 over 3 to the nth power. Now this I recognize as an alternating sequence. It's oscillating between plus and minus. And so I'm going to make use of the second theorem right here, which says that when a sequence is bounded above and below, that means it's oscillating the limit of the absolute value. If the limit of the absolute value of the sequence is finite, then the limit of the non-absolute value version will go to the same value. And so that's what I want to investigate. And so I'm going to look at the limit of the absolute value, which is the limit as n goes to infinity of n plus 1 over 3 to the nth power. So this is another infinity over infinity scenario. So using L'Hopital's, we have the limit as n goes to infinity. The derivative on top is 1, and the derivative on bottom is 3 to the n natural log of 3. And so now the limit clearly, the bottom gets bigger and bigger, and so we have 1 over a larger and larger number, which approaches 0. And so that means that our sequence converges. In part E, we are looking at the sine of pi over n function. And so here I want to consider the limit as n goes to infinity of sine of pi over n. Now this is a function within a function. You've got pi over n contained inside the sine function. And so I can view this as sine of the limit as n goes to infinity of pi over n. And the limit as n goes to infinity of pi over n, this is pi over a bigger and bigger number, which approaches 0. And so this is sine of 0, which is 0. And that means that this converges. And that makes use of the third theorem, which is appropriate when you have a function within a function. And so this says essentially that if the limit of what's inside is finite, then the limit of the outside is the function evaluated at that limit value. And so that's what we did. We combined both of those into one shot. And finally, we get to F, and that says we have a sequence n factorial over n to the nth power. So this is a little tad more complicated. And so in this one, our a sub n is n factorial over n to the nth power. So it's important to keep that one in mind. So you could think of this as n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. And you've got n times n times n and that you have n values on bottom. Now notice that this numerator we also could have viewed as 1 times 2 times 3 times 4 all the way up to n. And that is going to actually be a more useful way of perceiving this. So I'm going to continue with that approach, and I'm going to portion this out as 1 over n times 2 times 3 times 4. So the product 2 through n, and on bottom you have n times n times n. You have n minus 1 n's. And so I'm pulling just that piece outside. Now, n, we know, is going to be sufficiently large, and that means that this is a product of a bunch of fractions. The largest term, n over n, is 1, and so this is definitely going to be less than or equal to 1. And it's good to keep that in mind. So that means that that our an we know is going to be bounded above by 1 over n, and that 1 over n is this one here, and we know that it's bounded below by 0, as there is no term, and that's a strict inequality, by the way. Here we go. We know that it's never going to be 0. It gets close, but it'll never be 0. And so what's useful about this is that I realize that the limit as n to infinity of 0 equals the limit as n to infinity of 1 over n. Both of these limits are 0. So if the limit of the lower bound and the limit of the upper bound are both 0, then by the squeeze theorem, the limit of n factorial over n to the nth power must also be 0. Which means that this sequence is convergent. So let's see. There's one more problem that's left here. Yep. And so here we want to show that the sequence 3 over n plus 5 is a decreasing sequence. And so that means that the n plus 1 term is smaller than the nth term. So if it's decreasing, then an, as it relates to an plus 1, must share this relationship. And so the next term has to be smaller, or no bigger, certainly, than an. And so now we plug in. We've got 3 over n plus 5. And if n is n plus 1, then we have 3 over n plus 6 on the right. And so now I can simplify or manipulate, and I see that I could multiply n plus 5 to the right and n plus 6 to the left, and I get 3n plus 18 is greater than or equal to 3n plus 15. And if I subtract the 3n's and the 15, I've got 3 is greater than or equal to 0, which is true. And so that shows that it is decreasing. And there's different philosophies on this. I like following through to the end like I did here, but some people point out that the numerators are constant in this step 2 here, and the denominator is bigger on the right than on the left, and so you're dividing by a bigger number, and so that fraction must be smaller than the left side. So depending on who you're giving this work to, just be sure of how they like your final answer to be reported. But that is just a collection of things that you can do with sequences. Next up is series.